Hi all, in this video we will start with second module. The main topics in this module is IDEA and AES. IDEA means International Data Encryption Algorithm and AES is Advanced Encryption Standard. So in this video we will mainly learn the IDEA algorithm, which is a symmetric encryption algorithm. These are the contents: introduction, principle, working, rounds, output transformation, subkey generation for round, IDEA decryption, and strength of IDEA. Introduction. International Data Encryption Algorithm is one of the strongest cryptographic algorithms launched in 1990, but it was not that much popular as DES, which we have already learned, Data Encryption Standard, because this IDEA is a licensed version, so it is not that much popular. DES has a long history as compared to IDEA. The main application of IDEA is in the email privacy technology known as Pretty Good Privacy, PGP. Principle of this algorithm: IDEA is a block cipher. Like DES, it also works on 64-bit plain text block. So the block size is 64-bit, but the key size is 128 bits. IDEA is reversible like DES, that is the same, which means the same algorithm can be used for decryption. IDEA uses both diffusion and confusion for encryption. So diffusion means spreading of the plaintext bits over the ciphertext bits in order to increase the avalanche effect. Then confusion means it is making difficult to understand the statistical relationship between the key and the ciphertext. Working of the algorithm. The plaintext block is of size 64-bit. This 64-bit is divided into 4 portions, each of size 16 bits, from P1 to P4. P1, P2, P3, P4. These are the inputs to the first round of the algorithm. The algorithm has 8 rounds, 8 identical rounds. The key used here is of 128 bits. So this algorithm has to convert, every encryption algorithm has to convert a plain text into ciphertext. So with the help of the key. So plain text here, the plain text block size is 64-bit. It is divided into 4 portions, P1, P2, P3, P4, and then the key size is 128 bits. In each round, 6 subkeys are generated from the original key. So each round requires 6 keys for the encryption. So these 6 keys are generated from the original 128-bit key, and the size of each subkey is 16 bits. The size of the plaintext portion also 16-bit, and the size of the subkey also 16-bit. These subkeys are applied to the 4 input blocks P1 to P4. Thus, for the first round, we will have the 6 keys K1 to K6. Then for the next second round, we will have K7 to K12. Similarly, it continues. And for the 8th round, 8 6 are 48. So for the 8th round, we will have the keys K43 to K48. So for 8 rounds, we require 48 subkeys. After the 8th round, there is a round called output transformation. Thus, this is the final round. It uses only 4 subkeys, K49 to K58. So total K52. So total keys required is for the algorithm is 52. 52 subkeys are required. So these 52 subkeys has to be generated from the main key of length 128 bit. Each subkey is of length 16 bit. So after the output transformation round, the final output is produced. So this output is represented as C1, C2, C3, C4, each of 16 bits. So total 64-bit ciphertext block. Working. This is a general block diagram of the IDEA algorithm. So we can see here that the input to the algorithm is plain text, input plain text. The block size is 64-bit. It is divided into 4 portions, which is P1, P2, P3, P4, each of 16-bit length. And the output here we can see it is 64 bits. Output ciphertext is 64 bits. So this after the output transformation round, we can see that C1, C2, C3 and C4. These are combined and written over here. So there are 8 rounds, round 1, round 2, etc. up to round 8. After the 8th round, it is the output transformation round. So each round, this plain text is one of the input and the other input is the keys. So each round, 6 keys are provided. 6 sub keys are provided. So first round K1 to K6, second round K7 to K12, so on. And this output transformation round, only 4 keys are provided, not 6 keys, 4 keys are provided. So after this output transformation, we will be getting the ciphertext. So this is the general block diagram. Now we have to see what is happening in each of the rounds, inside each of the rounds. There are 8 rounds in IDEA and each round involves a series of operations on the data block and the keys. So the main operations are multiplications, addition and XOR operation. Similarly, same set of operations are performed for each round. For the next round, P1, P2, P3, P4 is changed to S11, S13, S12, S14. So here this S12 and S13, there is a swap between S12 and S13 to give the input to the next round. Input blocks for the next round are obtained from the previous round. These are the steps happening inside each of the rounds. There are 14 steps in each round. So we can see the steps one by one. So first S1, S2, S3, S1 to S14 steps are there. So inside each round, these 14 steps has to be performed. This includes multiplication, addition and XOR operation. These steps we have to remember. So S1 it is equal to P1 into K1. That is P1 multiplied by K1. So this side you can remember. S2 equal to P2 plus K2. S3, step 3 equal to P3 plus K3. S4 equal to P4 multiplied by K4. So this plain text blocks P1 to P4 and the keys. Each round has K1 to K6 keys as input. So this K1 to K4 is used here. Then next step S5, the S5 that step S1 XOR S3, then S6, S2 XOR S4. So this you can remember like this. You can write like P1, P2, P3, P4, then K1, K2, K3, K4. So first it is multiplication, then 2 additions, then multiplication. Then S5 equal to S1, S2 we can write here, S3, S4 we can write here, then XOR operations, 2 XOR operations. Then we have used K1 to K4 keys. Now we have to use the keys from K5 and K6. So this S7 equal to step 5 multiplied by K5. Then S8 equal to S6 plus S7. Then S9, here we can use the key K6 equal to S8 into K6. S10, steps 10 equal to S7 plus S9. Then step 11, 12, 13, 14, we can write S1, S3. Instead of S2, S3, you can write S3, S2, S4. Then S9 repeatedly you can write, S10 repeatedly we can write. Then this XOR operations. So these are the steps performed in a single round. And the output of this round is this one, S11. This is another output S12, S13, S14. This is given to the next round. So while giving to the next round, this S1, S11 corresponds to P1. Then S12 corresponds to P2, S13 corresponds to P3, S14 corresponds to P4. So while giving to the next round, here one swap we have to do. So first S11, then S13, then S12, then S14. So each round these two outputs are swapped before giving to the next round. So these are the 14 steps performed in each round of the IDEA algorithm. So now we can consider the 8th round. In the 8th round, the output is in P1, P2, P3, P4. New P1, P2, P3, P4 are taken in the same order, that is S11, S12, S13, S14. That same order it keeps. All the other rounds, the output is taken as S11, then a swap between these two. S11, S13, S12, S1, S14. But in 8th round, the same order is taken as the output. And after the 8th round, we can find a output transformation round. So 8th round, this 14 steps corresponds to the 8th round, and this is the output of the 8th round. It is given to an output transformation round. These are the transformation made by that round, that is P1 into K49, P2 plus K50, P3 plus K51, P4 into K52. So here output transformation round, we have already learned that it uses 4 keys. All the other rounds uses 6 keys. This round, the last round, uses only 4 keys. So these keys are used here, and the output from this is taken as the ciphertext. So C1, C2, C3 and C4, which is the ciphertext that is we obtained from the plain text using the IDEA algorithm. Each round consists of 14 steps. We have learned this. Each round can be considered as 2 parts. So among the 14 steps, steps 1 to 4 can be called as odd round, and steps 5 to 14 forms the even round. So another name it is given as odd round and even round. In each of the 8 rounds, this odd round and even round is there. Now consider the last round, that is the output transformation round. It is a one-time operation, takes place at the end of the 8th round. The output of this process is the final 64-bit ciphertext, which is the combination of 4 ciphertext blocks C1, C2, C3 and C4. We have already understood that how the plain text is converted to the ciphertext, and we have seen that in each of the rounds 6 subkeys are used. So our main key, there is one key of 128 bits. From this main key, we have to generate the subkeys for each of the rounds. So each round makes use of 6 subkeys. So total 8 rounds are there. So 8 6 are 48 subkeys are there. And the final output transformation round uses 4 subkeys. So total how many subkeys? 48 plus 4, 52 subkeys are required. So these 52 subkeys has to be generated from the main key, main 128-bit key. And the size of each of the subkey is 16 bits. The plain text part, that size is 16-bit. Similarly, the subkey size also 16-bit. So 128 divided by 16, we can have 8 subkeys in 128-bit. From 128-bit key can be divided into 8 parts of length 16 bits. That is K1 to K8. So 8 keys can be obtained from this 128-bit. Each subkey of size 16-bit. So the first round requires 6 keys. So from this 8, K1 to K8, 8 subkeys, 6 are given to the first round. So then 2 keys are remaining in the 128-bit key. This 2 keys will be given to the next round. For the next round, for the remaining round, subkeys are generated by performing key shifting. The original key is shifted left circularly by 25 bits. and hence 52 subkeys are generated. So the key, original 128-bit key, is left circular shift of 25 bits, which means the 26th bit will come as the first bit. And again that 128-bit key, after this left circular shift, it is divided again into 8 parts, and then previous round 2 keys are remaining, plus from this round 4 keys are taken, so total 6 keys obtained, and that is given to the second round. Similarly it continues and 52 subkeys are generated. Subkey generation for the first round. So in the first round, the original key is taken, which is of 128-bit length. It can be divided into 8 subkeys, each of size 16-bit. Among these 8 subkeys, first round requires only 6 subkeys. So 6 into 16, it is 96. Till 96 bits is used for the first round. 6 subkeys. So remaining bits, remaining 97 to 128, 32 bits are there, which are 2 keys are remaining, that can be given to the second round. Subkey generation for the first round. The initial key consists of 128 bits, from which 6 subkeys K1 to K6 are generated for the first round, each of length 16 bits. Since K1 to K6 consist of 16 bits each, out of original 128 bits, the first 96 bits are used for the first round. Thus, at the end of the first round, bits 97 to 128 of the original key, 2 subkeys, are unused as shown in the figure. Subkey generation for the second round. For the second round, again 6 subkeys are required. So in this, 2 subkeys are obtained from the first round. First round 2 subkeys are unused, that is given to the second round. Now it requires 4 more subkeys. So here it is shown that this is the unused bits of the first round, 97 to 128, which correspond to 2 subkeys, 32 bits, which corresponds to 2 subkeys. This will be given to the second round, and additional 4 keys are required. So for taking those 4 keys, the first operation it has to do is, the original key of 128 bit is left circular shift by 25 bits. 25 bits it is shifted. Then the 26th bit will reach the first position, and the circular shift means it will go to the right side. 25 bits will go to the first 25 bits will go to the right side. Then again, after this left circular shift, it is divided into 8 subkeys. And among these 8 subkeys, the first 4 subkeys are given to the second round. From the previous round, 2 subkeys are there, plus from this round, 4 subkeys are there. That is 4 plus 2, 6 subkeys are given to the second round. Then again, after taking 4 subkeys from this, 4 subkeys means it is 4 into 16 bits will be used, that is still 64 bits. Then again, after taking 4 subkeys from this 8 subkeys, then unused keys will be 4 again 4. This 4 subkeys will be given to the next round. So like this it continues. We can see the explanation. In the second round, firstly, the 32 unused bits or 2 keys of the first round are used. As each round requires 6 subkeys K1 to K6, each of 16 bits, making a total of 96 bits. Thus, for the second round, we still require 96 minus 32, which is equal to 64 more bits, that is 4 more keys. However, all the 128 bits of the original key are exhausted. For remaining 64 bits, IDEA employs the technique of key shifting, which is the left circular shift by 25 bits. The 26th bit of the original key moves to the first position. The whole process is shown in the figure. Once again, we can see the subkey generation for all the rounds, that is from first round to 8th round, and also for the output transformation round. So here is the subkey generation from the 128-bit key. So first, the 128-bit key is divided into 8 subkeys of 16 bits. So this is the 128-bit key is represented like this. It is divided into 8 subkeys, each of size 16-bit. This happens in the round 1. So round 1 requires only 6 keys from this. So these first 6 keys are given to the round 1. Then this 2 keys, 7 and 8. 2 keys means it will form 16 into 2, 32 bits. So these 2 keys is given to round 2. So it will come to the round 2. Then round 2 requires again 6 subkeys. So this 2 from here, and it should get 4 more subkeys. It has to generate. So for that, what it is done is, again this 128-bit original key, first it will be left circular shift of the original key by 25 bits. This is to provide some randomness. So this first 25 bits of this original 128-bit key is just left shifted. Left shifted means this 26th bit will become the first bit, and this 1 to 25 will go to the right side. Then again, after left circular shift, it is again divided into 8 subkeys. And from this 8 subkeys, only first 4 is taken and given to the round 2. 4 from this, and the unused 2 subkeys from the first round. This 4 plus 2, 6 subkeys is given to the round 2. Again here we can see that this 4, right side, this 4 subkeys are unused. It will be given to round 3. So round 3 again, this 4 will be given. It requires 2 more subkeys to make it 6. Each round requires 6 subkeys. So before dividing it into different subkeys, again left circular shift of the 128-bit original key by 25 bits. So again from this round, whatever it is obtained 128, after shifting we have obtained this 128-bit key. Again it is left shifted 25 bits. Again it is divided into 8, 4 from this round, and it requires only 2 from the third round. So 4 plus 2, 6 subkeys that will be given to the round 3. Then here also we can see that after taking 2, here it is 8 minus 2, it is 6. 6 subkeys are unused. It can be given to the next round. So round 4 will be getting 6 subkeys. 6 subkeys means it should not require any further subkey. It's adequate because each round requires 6 subkeys. So these 6 subkeys are given to the round 4. Again in round 5, it requires 6 subkeys. So it is not getting any pending keys from the previous rounds. So it has to generate from this only. So again left circular shift of the 128-bit key by 25 bits. From this round, again that 128-bit already left shifted. Again it is left shifted by 25 bits. Then again divided into 8 subkeys. 128-bit key is divided into 8 subkeys. This round requires 6 subkeys. So this 6, it is not getting any unused subkeys from the previous round. So round 5 will require 6 subkeys, that is taken from this 6 subkeys. So again 2 subkeys are unused, that will be given to the next round, which is round 6. You can see the remaining rounds. So round 6, 7, 8 and the output transformation round. So in round 6, how many keys it will require? It will be getting 2 unused keys from the round 5. Then it will do the left circular shift of the 128-bit key by 25 bits. After that, it will divide it into 8 subkeys. From this, only 4 is required. 2 subkeys are obtained from the previous round, plus this 4 will make the 6 subkeys. So again, these 4 subkeys are unused, which will be given to the round 7. So round 7 will be getting 4 subkeys, 2 more required. So again, left circular shift of the 128-bit key by 25 bits. Then it will be divided into 8 subkeys. The first 2 subkeys are taken. Then 4 plus 2, it will obtain 6 subkeys. Then again, this 6 subkeys are unused here, which will be given to round 8. So round 8 also similar to round 4. It has obtained 6 subkeys, which is enough for this round. So this 6 subkeys will be, which is obtained from round 7, is adequate and used in this round. No bits are unused. Then for output transformation round, it will not get any subkeys from the previous round. So it will do the left circular shift of 128-bit by 25 bits. So every round this process is doing left circular shift of 128-bit key by 25 bits except the first round. After that, divide that into 8 subkeys. From this output transformation round, which is the final round, requires only 4 subkeys. So 4 subkeys will be taken from this, used in output transformation round. Subkey generation for the output transformation round. The process for the subkey generation for the output transformation is exactly similar to subkey generation process for the other 8 rounds. At the end of the 8th round, the key was exhausted. Hence, the key is again shifted by 25 bits. After this, the first 64 bit of the key, which means 4 subkeys K1 to K4, is taken for the final output transformation. Now we have finished with our encryption process. So encryption, the plain text, how it passes through all the 8 rounds and the output transformation round, and ciphertext is formed. And each round 6 subkeys are provided. Then output transformation round 4 subkeys are needed. So after this encryption is over, now we can see about the decryption using this IDEA. The decryption process is exactly the same as the encryption process. There are some alteration in the generation and pattern of subkeys. The decryption subkeys are actually inverse of the encryption subkeys. Strength of this algorithm IDEA, it uses 128-bit key, which is double than key size of DES. DES key size is 64-bit, so this is the double of that. Thus, to break into IDEA, 2 raised to 128 encryption operations are required. Thank you.